In this stream, we're going to focus on the magnitude of the equilibrium constant, on some properties of the equilibrium constant, and we're going to practice the ICE table, calculating equilibrium concentrations and representations of equilibrium. I also added a free response question at the end. Okay, so as you already know, the constant of equilibrium is products divided by reactants, and you have the concentration of the species, the brackets mean concentration, as you already know, and the coefficient turns to the power in the equation. So it's the concentration of the products to the power of the coefficient over the concentration of reactants to the power of coefficient. And this, when you have numbers for K, what does these values mean? A value for K greater than 1 means that the equilibrium, it's far to the right. What does that mean? It will mean that the denominator is greater than the numerator is greater than the denominator. So at equilibrium, you will have present more products than reactants, right? Now, something to consider here is that even though we will have mostly products, we will still have always a bit of reactants, because at equilibrium, all the species, well, reactants and products will be present. That's what equilibrium means, the double arrow. A value of K less than 1 will mean that the equilibrium is far to the, I'm sorry, there's a mistake here. It should say far to the left. So at equilibrium, far to the left, so you will have mainly reactants at equilibrium. Again, it doesn't mean that you won't have products. You will have products, but you will have reactants in more amount, in a greater amount. Now, also something important to consider for K, even though if the K is a big K, it doesn't mean that it will be a fast reaction. The size of K and the time needed to reach that equilibrium position are not directly related. The speed of the reaction is more in the order of kinetic. Okay, some properties of the equilibrium constant. The value of K can be calculated easily if your reaction is manipulated, if your equation is manipulated. For example, here we have 3 examples. The regular reaction, in which, as we mentioned, is products to the power of the coefficients over reactants. But if we have the reciprocal, now, as you notice, these are the products, and now we have them as reactants. So if they ask you to calculate for K for the reversible reaction, we just do the inverse of K, because that's what we're doing. The manipulation is shifting the numerator to the denominator. And by doing the inverse, that's what we're doing. And if the equation is raised to another, if multiplied by another coefficient, then you just raise the original K to the power of the coefficient that was multiplied originally. And that's some ways that you can modify K to match with the modification on the equation. Questions? No. Okay, we're going to continue. Okay, let's do an example with these manipulations. Consider the reaction coefficient 2 of NaOCl in equilibrium with 2 nitrogen monoxide plus chlorine gas at 35 degrees Celsius. And they're telling us that after the system has reached equilibrium, the concentrations are observed to be the following. We have the concentration of the 3 species. And it's first asking us to calculate the value of K, the regular K. So we're just going to do products to the power of the coefficient over reactants to the power of the coefficient. And remember that K is given with no units. And then they're asking in letter B, calculate the K for this reaction. And if we notice, it's the reverse reaction. Now these are the reactants here, and what was originally a reactant is now the product. So what do we do? How do we solve for K now, for letter B? Exactly, Mireya, we do the reciprocal. Correct. And that's how we get the number. And it makes sense that the reciprocal, if the original has a very small k, of course, the reciprocal will have a big K. So that's a way to double check that it makes making sense what we're doing. And now here in letter C, they're asking us to calculate K for this reaction. And as we notice, the coefficients are different. How different? We will have to multiply times 2, right? The original equation. So what do we do to the K? Correct. We raise it to the power of that, we're doubling, so we raise to the power of 2 in this case. And that's how we solve this. Okay, so another property of the equilibrium constant is the when we have multiple reactions, like in reaction mechanism, when we have several reactions that will give you the overall. The equilibrium constant for a net reaction made up of 2 or more individual steps, remember the elementary steps in kinetics, would be the product of the equilibrium constants of each step. So if they gave us 2 equations with their proper K, and as you notice, the overall equation is the addition of these 2, because the BR, what would the BR be called if we remember our kinetics concepts? Bromine. If this is a reaction mechanism, what would bromine be? Correct. Very good, Mireya, an intermediate. So we're reviewing kinetics on the same string. So correct. So now the K, it says that the individual, the net reaction would be the product of the equilibrium constants of each step. So K3 would be just the product of K1 and K2. And again, remember, no units for K. Questions? No, right? Pretty easy. Okay. Now we're going to talk about Q. Q, it's called the reaction quotient. And it is calculated the same way as K, products over reactants, but we're going to use initial concentrations instead of equilibrium concentrations. And the Q is very useful in our problems when we do the ice tables, because sometimes it's not that obvious if the reaction will go to the right or to the left. So that's how we use K. We use, Q. We compare it with K to decide the way the equilibrium will be moved. So if they're equal, then it means that the system is already at equilibrium. So no shift will occur. If K is smaller than Q, then the reaction starts with more products, because this is bigger, so this one has more products. The numerator is bigger, so the system will end up shifting to the left. And if the contrary, if K is greater than Q, then the reaction starts with more reactants than products, and the system will shift to the right. This is going to be very useful again in the ice tables. So this is just the same thing that we said, but with a visual. If K is bigger, and then this means that the denominator is bigger on Q, so it has more reactants, it shifts to the right. At equilibrium, they're equal, and the contrary, when it has too much product to start with, then it will shift to the left. Any questions here? Any questions about the meaning of Q and K? Okay, let's start with a problem. So in this example, we have the temperature at 700 Kelvin. Carbon monoxide reacts with water to form carbon dioxide and hydrogen. Here is the equation. They're giving us the equilibrium constant, 5.10. And then we're going to consider an experiment in which 1 mole of carbon monoxide and 1 mole of water are mixed together in a 1 liter flask. Calculate the concentrations of all species are equilibrium. So here we're going to use a rise table or an ice table, correct? So we place the reaction. We use our data for the initial concentrations. And here it's obvious that the reaction is going to shift towards the products because we have non-zero products. The change, we show it with X. So these ones are going to decrease by a factor of X, while these ones is going to increase. These X are because the ratios are in a 1-to-1 ratio. So that's why we just place X. If there would be a coefficient here at 2, then it would be plus 2X. Right? So then at equilibrium, we just place the initial minus the change. And then what do we do next? What do we do next, Mireya? What would be the next step? Solve for X. Yes, but correct. Solve for X using we have to place the expression, the equilibrium expression, right? And then place using the value given of K, exactly. And then solve for X with your calculators. Right? You usually get 2 or more values in the calculator, but then it's easy to figure out which one is the correct X. For example, here, which one would be the correct X? 0.693 or 1.79? Excellent, correct. Because 1.79 will give you a negative value here, right, for the two reactants, and we cannot have a negative concentration. So correct. Once we decide our X, we just solve for the individual concentrations. So we will have carbon dioxide and hydrogen to be 0.693, and 1 minus that number, so 0.307 would be the molarity for carbon monoxide and water. Questions? Okay, let's continue with another example. So in example number 4, now we have this reaction of hydrofluoric acid or hydrogen fluoride, because it's gas, not aqueous. If it was aqueous, it would be hydrofluoric acid, but it's only hydrogen fluoride, decomposes to hydrogen gas and fluoride gas. They're giving us a value of K that is bigger than 1. And it says they're giving us 2.50 moles of HF, 2.50 moles of hydrogen, 2.50 moles of F2 fluoride, are mixed in a 5-liter flask and allowed to react to equilibrium. So for the equilibrium concentrations, what should we do first? What do we need on the, correct, the ice table, but what do we need in the ice table? We need concentrations. We have moles and liters. So the first thing that we need to do is to get the, right? We need to get the molarity of the species involved, correct? So, right, we divide that 2.50 by 5 liters, and that's for all the species. So we have these values. Maybe it's not so evident now in which direction will the reaction shift. So what do we need to do to figure out if this is minus X plus X plus X or plus X minus X minus X? How do we decide? We solve for, remember, we said a while ago. We solve for Q, the reaction quotient. So we solve for Q because maybe in here it's not so obvious how will the equilibrium will shift. So we solve for Q with the initial concentrations, and Q is 1. So K is greater than Q, so the reaction will shift right. So then we decide minus X because this will go to the right, and we have to consider the coefficients. If it would be different, if it would be I'm sorry, I lost the straight. Okay, if it would be Q greater than K, then we will have to do plus 2x minus x minus x. So usually when they don't give you products, then it's obvious it's going to shift to the right. But if they give you concentrations of all the species, please don't forget to solve for Q first, because there's some tricky questions that, correct. That Q will determine if the change is negative for the reactants and positive for the products, or the other way around. Exactly. Very good. Any other question here about Q and K? That's why it's important, the reaction quotient, and that's why it's important to have in mind what does a big K means and a small K. Okay, so once you decide that, then you continue with the equilibrium calculations as before. You use the given K, okay, and you solve for X. You solve for X, and again, you get two values. And then you decide which one makes more sense. These ones are pretty close. But if you solve for 0.289 in the concentration of HF, you will get a negative value. Since it doesn't make sense to have a negative molarity, then your X value is the other one, 0.214. Once you decided the X value, then you solve for the concentrations of all the species at equilibrium. Representations of equilibrium. This is usually particle representations of equilibrium. For example, it says here, consider the reaction of water plus carbon monoxide in equilibrium with hydrogen and carbon dioxide, and they're giving us the value of K. And you have a particle diagram here. You have water and carbon monoxide. Usually they give you a label of the species. And it says, when concentration is achieved, how many molecules of all species are present in equilibrium? How would you solve this problem? The way to do it is with trial and error, but also another way to do it is, again, to use our ICE table. And right, count the number of water and carbon monoxide and set up a rice table. Yes, right, Sigib. Sigib, yes, right? Okay, so correct. I have 1, 2, 3, 4, 5, 6, 7, 8 water molecules. 1, 2, 3, 4, 5, 6 carbon monoxide molecules. So that would be our initial concentrations on the rice table, right? And then since the products are 0, it's obvious that the reaction will shift right. And then we do the equilibrium. We set up our equilibrium expression with the value of K. Solve for X, and we have X equals 4, X equals 24, and 24 is too big. It doesn't make sense. It will also give us negative concentration. So we choose 4, and now we have the values for each. Now, what do we have to be careful when doing particle representations? One thing is the stoichiometry, which we already got the amounts of each, but what's another thing that we need to, the hydrogen concentration, Mireya, would be 4. But what are other things we need to consider? For example, let's go back to the original problem. What do you notice of water here? Why didn't they place the hydrogens aligned to each other? Why didn't they move the hydrogen here? What are they showing when they do the water in this? No clue? They're also showing the VSEPR shape and the angles. Remember that water has a bent shape, and all molecules that are only with 2 atoms are linear. So you have to also be careful when you're doing particle diagrams to also show the angles as good as possible. So hydrogen, H2, what shape would you think it'll have? It's only 2 molecules, so it would be what? According to VSEPR? Linear, correct. And what about carbon dioxide? Do you know the VSEPR shape of carbon dioxide? Okay, if you do the carbon dioxide Lewis structure, you will notice that it has a double bond. So it would end up being linear as well. So once you have all the quantities, you have to make sure you place the proper value. So 1, 2, 3, 4 waters, 1, 2, 3, 4 carbon dioxide, and 1, 2 carbon monoxide, and 1, 2, 3, 4 hydrogens. Notice how I draw here the carbon dioxide as linear, right? So that's things that you need to consider when you're doing particle diagrams. Make sure the stoichiometry makes sense. Make sure you're showing the correct law of conservation of mass. Nor you have to have the exact same amount of spheres representing elements, and as much as you can, try to show the proper VSEPR shapes. They're going to look into that when they're grading your exam. Okay, questions on this representation of equilibrium? Okay, now that would be like if you forgot about the VSEPR shape, there's some rules, right? 2 and 2, linear, remember? 4 and 0, tetrahedral. I think that would be something to consider having in your notes, because a lot of VSEPR and intermolecular forces, I think that it's always a big chunk on the exam. I think it will also be for this one. Okay. Okay, now it's time for our free response question. I was struggling finding a free response question that was available to the public, and that it also was about equilibrium. This one right here is more about equilibrium of gases, and instead of the Kc for concentrations, for this one we're going to use Kp, but I still think it's a valuable example and a valuable review. So let's work this out. So we have the reaction of calcium carbonate in equilibrium with calcium oxide and carbon dioxide. Notice that the species here, you start with a solid, and then solid and gas. What do you remember about the K expression when you have solids? When you have, this is called, remember, heterogeneous equilibrium. When you have of different species what changes for the K? Do you remember? Correct. Correct, Mireya. You never use pure solids or pure liquids. So what would be the K? The K of equilibrium, because it's a gas and they're showing pressure, it would be Kp. What would be the expression? Just by looking at the equation, you can determine the K expression. Carbon dioxide, it's a gas, correct? But calcium carbonate, it's a solid. Should we include it on the expression? Excellent. So you don't use it on the equilibrium expression. So the equilibrium expression would only have carbon dioxide. And okay, so it says, when heated, calcium carbonate decomposes according to the equation above. In a study of the decomposition of calcium carbonate, a student added a 50-gram sample of powder calcium carbonate to a 1-liter rigid container. The student sealed the container, pumped out all the gases, then heated the container in an oven at 1100 Kelvin. As the container was heated, the total pressure of the carbon dioxide in the container was measured over time. The data are plotted in the graph below. So since the student pump out all the gases, it starts at 0, and then it goes all the way to a little bit more than 1 atmosphere. Where, by looking at the graph, at which time do you think equilibrium was achieved? Okay, yes, it will be equilibrium until this one is flattened, right? So more around here. You mentioned, Mireya, 10.4 minutes. That would be here. So if you go slightly more, like, I don't know, like 12, 13 minutes, right? Would be when equilibrium will be reached. Yes. Okay, then it says the student repeated the experiment, but this time the student using 100 grams instead of 50 grams sample of powdered calcium carbonate. In this experiment, the final pressure in the container was 1.04 atmosphere, which was the same final pressure as in the first experiment. So it says, letter A, it says to calculate the number of moles of of carbon dioxide present in the container after 20 minutes of heating. How would you solve this question? How would you get the number of moles? Carbon dioxide, it's a gas. What do you have for information about the gas? You have the pressure and you have the volume of the container. You also have the temperature. So how would you solve it with this data? Exactly, very good. You will use the ideal gas law, PV equals nRT, and then solve for N, which is moles. And correct, with these values, and you use the value of for R that it's in the AP constants and equation sheets. I always, this is a trick that I always do. I always leave R at the end. Why? Because then I can place, like, more visual for me, the units of the R. Instead of doing the negatives, I like this better. So I'm giving you this tip if you like it. And then you cross all the units that are above and below the fraction, and that's also another way to check if you are solving for the correct thing. And here, yes, the only one that we didn't cross is moles. So, and make sure you consider the proper sig fix, and that's it. Pretty easy, right? Okay, letter B on this problem, it says the student claimed that the final pressure in the container in each experiment became constant because all of the calcium carbonate had decomposed. Based on the data of the experiments, do you agree with this claim? Explain. I'm giving you the answer here. Sorry, I forgot to place a blank slide without the answer. But read the answer, Mireya, and let me know if it makes sense. Yes, right? So do not agree with the claim. Both experiments reach the same pressure. So the amount of, so increasing the amount of calcium carbonate did not produce more product. So not all of the calcium carbonate reacted. The reaction reached equilibrium, and there must be some calcium carbonate left in the container, as always in equilibrium equations, right? There's always present some reactant and some product in the reaction vessel. And letter C, after 20 minutes, some carbon dioxide gas was injected into the container, initially raising the pressure to 1.5 atmosphere. So you're adding more product. So what will happen? The equilibrium will shift to the left momentarily. And it says, will the final pressure inside the container be less than, greater than, or equal to? Explain your reasoning. And again, I'm sorry that I show you the answer right away. But the answer is that the final pressure inside the container will go back to equilibrium. So it would be equal to 1.4 because the equilibrium is Kp equals the concentration of CO2. So when more carbon dioxide was injected, the reaction will be shifted to the left to achieve equilibrium at the same value of K. So the amount of carbon dioxide in the container will decrease until the pressure goes back to 1.4. So the equilibrium was disturbed because more carbon dioxide was added, so the reaction shifted left. So the pressure of 1.5 will be decreased to the 1.04 pressure at equilibrium. You were comparing it to the explanation of Q and K. Sure, you can do that because now your Q is bigger, correct? So it will shift left. Yeah, that's another way to see it, Mireya. Very good. Does it make sense? Okay. There's another one. Are there sufficient data obtained in the experiments to determine the value of the equilibrium constant, Kp, for the decomposition of calcium carbonate? At that temperature, justify your answer. And the answer is, again, yes. Again, I apologize for showing the answer right away. So since the equilibrium constant of Kp only it's a determinant in carbon dioxide, then the pressure of carbon dioxide, sorry, another typo. This should be a capital O. The pressure of carbon dioxide at equilibrium determines the value of K, which is the pressure of carbon dioxide, which will equal 1.4. So we did have enough data because they showed us the graph, right? Where at equilibrium, the pressure is 1.4. Right. And I think, yeah, that was it. Any questions, Mireya? So for the answer, do we also add 1.4? Let me go back to that. Okay, so the justification is where you have to specify that the Kp equals the will only be determined by the pressure of carbon dioxide at equilibrium. So since they gave you the pressure of carbon dioxide is 1.4, that's all you need to determine the K. There's nothing else that you will need. As long as you explain it, you don't actually have to give the value, but since you have it, do it as much. What I recommend you on the justification is give as much detail as possible. Any questions? Okay. Is there anything else that you would like to review? Anything else that you struggle for equilibrium? Or any topic, like we still have time if you need something else. Thermodynamics. Okay, what do you need about thermodynamics? Just an overview. Okay, for thermodynamics, you are going to, thermodynamics is the study of heat, right, on the equations. So what the questions are going to be related to, if it's exothermic, if it's endothermic, if calorimetry as well, which the main, let me see if I can, what is the main, do you remember the formula for calorimetry? Okay. So if we want, for example, a quick review of thermo. Correct. Correct. The Qmat. Q will equal to MC and delta T. Correct. Well, I'm going to write delta, but you know that it's the triangle. Correct. M is for the mass, correct? And C would be the specific heat. Do you remember what the specific heat means? The specific heat of substances means how much heat, or how much heat the substances have to absorb to be able to increase its temperature in a degree Celsius. So for example, water, it's better explain the specific heat with water, because water has a very high specific heat compared to other substances, because it's able to absorb a lot of heat before raising its degree temperature. For example, if you are going to you're going to make a cup of tea, it takes a while for the water to heat up. Contrary to, for example, a metal, if you place a spoon directly to the fire, you will have to let it go right away, no? Because it will, the metals will have a very low heat capacity, right? So that's the concept of heat capacity, of the specific heat capacity of the compounds. And delta T will be just the change of temperature. So for example, in a calorimeter, which was usually the one of water, the Q of water would be equal to negative Q of whatever thing that you're placing in the calorimeter. For example, if you're placing a metal in the calorimeter, let's suppose, then whatever the heat the water gained, you assume that it was the heat that the metal lost. So that's why it's placed a negative here to show that the gain of the heat of one substance, in this case water, will be the loss of the other substance, which is the metal or whatever. So that's how you show with the negative that the changes are loss of heat will be the gain of heat for the other one. And usually they give you the specific heat of water, the mass of water, the mass of the metal. So you first solve for Q, and then you equal to the Q of the metal or whatever other substance they're giving you. Usually they give you the mass of the metal and the change of temperature, and usually they ask you to calculate for the specific heat of the metal, or sometimes they ask you to solve for the final temperature that the system will gain. So it's actually pretty easy. And what else can they ask you? They can ask you right, things about exothermic, endothermic, which of course you know, right? When a reaction is exothermic, it will release heat. That's very simple. I don't know what other things can I help you with. Gibbs free energy. That's a good question, Caitlin. The only, like, the last units of equilibrium touch a little bit Gibbs free energy, but only on the sense of explaining, for example, for dissolutions, you have to look at when you have a substance like salt, a salt that is going, let me unshare my screen so that it's, let me see here. Okay, or maybe I didn't set up that, so that I can write something, but maybe I can write it in, let me see. Okay, let me see if I can make myself clear with this. If you have, for example, a salt, let me, I have here water. If you have a salt and you dissolve it in water, think of the salt, and a salt would be an ionic compound that is very tightly packed. What does the ionic substance has to do to be able to dissolve in water? I think that the questions that they're going to ask you are going to be in if a salt is soluble in water in terms of entropy and free energy. And for example, entropy refers to how the system, remember that entropy is like a concept of chaos, of more disorganizations, correct? So the ions will dissociate, Caitlin, thank you, yes, you're correct, will dissociate and will separate, and that will cause a greater entropy than they were to start with, because they were more organized and then they disorganized. So that would be an increase in entropy, right? And the water molecules also, they're not as tightly packed as the ionic, because they are, a liquid is not so organized, but they still have some organization with the hydrogen bonds. So also the water has to open up to give space for the salt, for the ions to merge between the water molecules. So the water giving space for the ions is also an increase in entropy, right? But then when everything comes together with the salts, with the ions of the ionic salt and the water, then the entropy decreases, right? So you're just going to be the problems that I have seen on that regard is that they tell you the values of entropy, the S, and of the free energy, the G or the delta E, G, and you will have to compare the values to determine if the reaction will be spontaneous, will occur on its own, or it would be thermodynamically favorable or no. There's a chart that I'm sure you can find on your textbook where they give you values of S, of entropy, and values of temperature and values of G. And there's a formula on the constant sheet where you have the, let me bring it up. Okay, so this equation is, well, here you have the QMCAT equation, and this one. So you will just, like a reaction would be spontaneous if the delta G is negative, and it would be spontaneous if the delta S is positive. So they're going to give you different values of G and S at a certain temperature, and maybe H enthalpy as well. And you will have to decide if the reaction is spontaneous or if the dissolution is thermodynamically favorable. So you can use these values. You can take a look at the chart. You know which chart I'm telling you about? It's a chart that says if this is positive and this is negative, it will be spontaneous. There's a chart that I'm sure you can find in your textbook. So take a look at that, and then that would be the explanation of why some salts, ionic salts, dissolve very easily in water, and some do not. For example, there are some salts, especially salts that are, for example, with a big charge, like calcium salts that have a positive 2. Remember that when the salts don't dissolve in water, it's because they prefer to be together. They prefer to be close to each other. So it depends on the charge. Remember Coulomb's law, and also depends on the radius of the ions. If the ions have a big charge and a small radius, most likely they will be together. And if not, they will dissolve, like salt in water dissolves very easily. But it also has to do with the concept of entropy and free energy to be able to do the dissolution. I don't know if this helped. Okay, so find that table and have it at hand, and read a little bit about the definition of entropy, that it's like the universe, the entropy of the universe is increasing. It means that the universe prefers to be like in chaos than organized. And take a look about free energy, and then using those equations, this equation, you can do this concept, you can do these relationships. Okay, any other thing that I can help you with? Okay, well, that's all from my part. At the end of the slides, you have my email. Sorry, I'm forgetting my words. If you have any other questions, you can email me, and that's all for me. Thank you. Bye. Good luck on the AP exam.